Welcome, curious minds, to a brand new deep dive.
Great to be diving in.
Today we're plunging into a really fascinating collection of sources. They explore some of the most profound and honestly perplexing questions in physics.
Absolutely. Real head scratchers.
So our mission really is to unpack the core ideas behind 10 of these, well, mind-bending paradoxes and unsolved problems.
Yeah, not just what they are, but digging into why they challenge everything.
Exactly, why they challenge our understanding of reality and, maybe crucially, what these big cosmic puzzles might mean for you. The sources, they have this blend,
Yeah.
deep science, but also almost meditative.
That's a good way to put it. Thought-provoking for sure.
So, yeah, prepare for some genuine aha moments. Going to stretch your mind a bit.
And that's what makes it exciting, right?
Yeah.
These aren't just abstract puzzles for academics. They really push the limits of what we can even know or measure.
Pushing boundaries.
Definitely. And what's fascinating is how they show the limits of our current science, our frameworks. Often they just raise more questions than answers, which is, well, kind of the point sometimes in science. A reminder there's still so much mystery.
A little humbling.
Exactly. So we really hope you join us on this intellectual journey. Think about your own take as we explore these ideas.
Okay, let's jump in. First up, Boltzmann Brains.
Yes. A classic.
So imagine the universe way, way in the future, almost empty, stars are out, entropy's kind of done its thing. And this is where it gets really weird.
Right. So in that near-empty, potentially eternal universe, the sources suggest that just by pure random chance, atoms bumping into each other over, infinite time, you could get molecules, cells, even fully formed human brains, identical to yours.
Identical, with memories and everything.
Exactly. With your consciousness, your memories spontaneously formed. And not just once, infinitely often.
Whoa, okay, that's a lot. How does something so random become infinitely often?
Well, if time is truly infinite, even incredibly improbable events become certainties, mathematically speaking. They happen an infinite number of times.
So the implication is, what? That we might be one of those random brains?
That's the disturbing question it raises. If a cosmological theory predicts way more of these random Boltzmann brains than observers like us who evolved normally, then maybe that theory's wrong. It challenges our confidence that we're not just a random fluctuation, it's a test for theories of the universe.
So it could actually invalidate certain models of the cosmos.
Yeah.
Just based on this statistical nightmare.
Pretty much. If the theory says random brains are more likely than us, something's fishy with the theory's picture of reality.
Okay, wow. Deep thoughts already.
Yeah.
Let's pivot slightly. To quantum theory. Why real numbers?
Right.
So quantum mechanics, describing the super small stuff, it famously uses complex numbers. Numbers with a real part and an imaginary part.
Exactly. The square root of -1 pops up everywhere in the equations.
But here's the thing the sources point out. Every measurement we actually make in the real world always gives us a real number. No imaginary components show up on our detectors.
And that's the puzzle. It's not just a mathematical detail. It kind of suggests that maybe part of physical reality described by those imaginary parts is somehow hidden from us.
Hidden. Or just. We can't measure it yet.
Could be either. Or maybe those imaginary parts are essential for the theory to work, for its internal logic, even if we don't directly see their effects. It implies, what we directly perceive might just be a slice of the whole pie.
A hidden reality. That connects nicely, actually, to the next one. The black hole information loss paradox.
Another big clash.
So quantum physics 101, basically. Information cannot be destroyed.
Right.
It can change form, get scrambled, but it never just vanishes.
That's a fundamental principle. Unitarity. Information is conserved.
But black holes, they seem to be the universe's ultimate shredders.
They certainly appear that way. Stuff falls in, and seemingly the information about it is just gone, wiped clean.
And Hawking radiation doesn't help.
Well, that's the twist. Hawking radiation is emitted, but the sources stress it seems completely random. Thermal. It carries no obvious information about what made the black hole in the first place.
So that creates a massive conflict.
Huge. Either quantum theory's rule about information always being conserved is wrong or incomplete, or our understanding of black holes, maybe rooted in Einstein's gravity, is fundamentally flawed. It's a direct collision between general relativity and quantum mechanics. One of them has to give or be modified.
High stakes indeed. Okay, sticking with those two pillars. Quantum gravity.
The holy grail, some would say.
Quantum mechanics, as we know, allows weird stuff. like particles being in two places at once. Superposition.
Yep, that's standard quantum weirdness.
But then you bring in gravity. Einstein's gravity describes space-time as this smooth, continuous fabric.
Right, a well-defined stage.
So how does that work if gravity itself is quantum? Does space...
And that's exactly the problem. Einstein's equations, as they stand, just can't handle a split gravitational field, a superposition of space-time geometries. It leads to contradictions.
So what's the question then? Is gravity special? Does it just not play by quantum rules?
Yeah, that's one possibility. Maybe gravity is fundamentally classical? Or the more common view is that both theories are incomplete, and we need a deeper theory, quantum gravity, to reconcile them. We're missing something crucial about how space-time behaves at the quantum level.
It's amazing how these two incredibly successful theories just break down when you try to combine them.
It shows where the frontier is.
Yeah. Okay, let's shift scale dramatically from the quantum to the cosmic. The Fermi Paradox.
Where is everybody?
Exactly. You look at the numbers, billions of stars, probably trillions of planets. And what we think we know about how life starts, biochemically speaking, it feels like it shouldn't be that hard.
Right. Common sense suggests the universe should be teeming with civilizations, advanced ones even.
But silence. We haven't detected any signals, any probes, any evidence. Nothing.
And that's the paradox. The sources mention a few possibilities. Maybe we're just not that special and nobody bothers with us.
Maybe.
Or maybe they are watching, like some cosmic zoo, the prime directive idea.
Star Trek again.
Or maybe they're out there, but they're waiting, hibernating, or waiting for us to mature, perhaps.
Or the great filter idea, that something prevents life from reaching that advanced stage.
That's the more sobering possibility, yes. That there are major hurdles, maybe one we haven't hit yet, or maybe one we've luckily passed. The silence forces us to question our assumptions about how common intelligence really is.
Yeah, the great filter always makes me pause. Okay, let's bring it back down to Earth. Sort of complexity and emergence.
This one's a bit different, less of a direct paradox, more of an observation needing explanation.
You see this trend everywhere, right? The universe seems to get more complex over time. Simple particles form atoms, atoms form molecules, then life, ecosystems, societies.
Even, as the source cheekily notes, YouTube reaction videos. It's a pattern of increasing organization and intricate structure.
But what is complexity, scientifically?
And that's the first problem. There's no single agreed-upon definition. And even more fundamentally, why do the laws of physics seem to promote this increase in complexity? It's not immediately obvious from, say, thermodynamics, which talks about increasing disorder, entropy.
So it seems counterintuitive.
In some ways, yeah. And the sources suggest understanding this emergence, how complex behaviors arise from simple rules, might be key to understanding really deep things, like consciousness itself. Maybe the tendency towards complexity is a fundamental aspect of reality we haven't grasped yet.
Like another law of nature, almost. Interesting. Okay, time for a classic. The grandfather paradox.
Can't talk paradoxes without this one.
Einstein's theories, general relativity, they contain solutions that look like they allow for time travel loops. Going back to the past.
Mathematically, yes. Closed time-like curves are possibilities within the framework.
But then comes the killer question. What if you go back and prevent your own birth? Kill your grandfather before he meets your grandmother, the classic example.
Right. If you succeed, you were never born.
Yeah.
If you're never born, you couldn't go back in time to do it. It's a flat-out contradiction.
So what stops it? Is time travel just impossible? Or does something intervene?
The sources discuss ideas like Stephen Hawking's chronology protection conjecture, basically saying the laws of physics somehow conspire to prevent these paradoxes. Or maybe the timeline self-corrects, you try to shoot grandpa, but the gun jams or you miss or something always happens to ensure consistency.
So reality has built-in paradox-proof armor.
That's one way to think about it. The debate really gets at the nature of causality. Is it fixed or flexible? The paradox forces us to confront that.
Fascinating. Sticking with time. Arrow of time.
Another deep one rooted in everyday experience.
Yeah, for us, time clearly flows one way. Forward. We remember yesterday, not tomorrow.
Yeah.
Eggs break, they don't unbreak.
Our psychological experience of time is strongly directional. The arrow points firmly towards the future.
But the fundamental laws of physics.
Most of them don't care. They work just as well run backwards in time as forwards. Newton's laws, electromagnetism, even quantum mechanics at the micro level. They're time-symmetric.
So where does the arrow come from? People always say entropy, right? Disorder increasing.
That's the usual explanation, yes. The second law of thermodynamics. Systems tend towards more probable disordered states. An unbroken egg is ordered, a broken one is disordered.
Uh-huh.
But the source points out this might be more of a description than an explanation. It restates the observation that things tend towards disorder, but doesn't necessarily explain why the universe started in such an ordered state in the first place, allowing entropy to increase. Some link it to quantum measurement, the collapse of the wave function, but that's also not fully understood.
So the arrow of time is still kind of mysterious, even with entropy.
There are definitely deep questions remaining about its fundamental origin. Why this stark difference between the laws and our experience?
Okay, next up, the probably most famous quantum thought experiment. Schrödinger's cat.
Ah, the poor cat. Both alive and dead.
The idea being, quantum effects like superposition, being in multiple states at once, shouldn't just be for tiny particles. They should, in principle, scale up.
If a radioactive atom is in a superposition of decayed not decayed, and its state triggers a mechanism to kill a cat, then the cat itself should end up in a superposition of alive and dead. Until we look.
But that's absurd. We never see cats like that. Or, zombie cats walking around.
Exactly. That's the point of the thought experiment. It highlights the clash between quantum description and macroscopic reality. So the big question is, why does this quantum weirdness vanish when things get big? Where's the cutoff?
What are the ideas?
The leading explanation is called decoherence. Basically, the quantum system, the cat in this case, interacts inevitably with its environment, air molecules, photons, whatever. These interactions rapidly entangle the system with the environment, effectively smearing out the superposition into the wider world, making it impossible for us to observe the pure alive and dead state directly.
So the environment kind of forces a choice.
It makes the superposition incredibly fragile and practically unobservable at large scales. It doesn't fully solve why a specific outcome occurs, the measurement problem, but it explains why we don't see macroscopic superpositions. It points to that fuzzy boundary between quantum and classical.
Still feels a bit like waving hands, but okay. Last one. A sci-fi favorite. The transporter paradox.
Beam me up, Scotty. Or maybe don't.
Right. So the Star Trek transporter, it supposedly disassembles you atom by atom, records all the information, sends that information somewhere else, and rebuilds you perfectly from new atoms. Is that you on the other side? Or just a perfect copy, while the original you died during disassembly?
This one hits hard on questions of identity. Now, quantum mechanics actually throws a spanner in the works right away with the no cloning theorem.
Oh, yeah.
You fundamentally cannot create a perfect, independent copy of an unknown quantum state without destroying the original. So a perfect Star Trek transporter, copying quantum states exactly, might be physically impossible.
Okay, so physics might save Kirk after all.
Yeah.
But let's ignore that for a second. Hypothetically, if you could make a perfect atom-for-atom replica.
Right, ignoring the no cloning thing. Does personal identity survive? Is it the atoms, the pattern, the information, the continuity of consciousness, the subjective experience, am I dying every time I beam? That remains the philosophical core.
And what constitutes you? It's such a fundamental question.
Exactly. It forces you to think about what makes you you. Is it your physical stuff or something more abstract like the pattern or the flow of consciousness? Science doesn't have a definitive answer for that subjective part.
Wow. Okay, that was quite a journey. 10 paradoxes, 10 deep dives into the weirdness of the universe.
From Boltzmann Brains popping into existence
to whether beaming down kills Captain Kirk. Yeah. It's incredible how these questions, some sounding almost like science fiction, really probe the absolute foundations of reality.
They really do.
We covered a lot of ground there. Hopefully you listening have grabbed some new insights or at least some fascinating new questions to ponder about, well, everything.
And that's really the value, isn't it? The sources we looked at emphasize this too. Engaging with these puzzles, even if they seem abstract or whimsical, it's actually fantastic training for thinking critically.
Developing problem-solving skills.
Exactly. It encourages structured thinking, curiosity. Just trying to wrap your head around these things sharpens your mind. So yeah, keep questioning, keep learning.
So the final thought to leave you with, maybe building on that.
Yeah, consider this. How can tackling these seemingly unanswerable questions about the universe actually make you better at approaching complex, maybe even messy problems in your own life? What new questions, big or small, do these paradoxes spark in you?